Alright, so I just want to go through some basic facts about graphs and calculus to keep this discussion reasonable. Let's suppose that I is a interval of R. So really a connected subset of real numbers, all right? Then if you have this, right, we have some connections between, well, for example, if A less than B implies f of A less than or equal to f of B for all A comma B in I, then f is increasing. Alright, 2. If A less than B implies that f of A is less than or equal to f of B, you know, again, for all A and B in the interval, then f is decreasing. Alright. Now, if the inequality doesn't allow equality, all right, then you could say strictly increasing or strictly decreasing. If a function is both increasing and decreasing, it's said to be constant, all right? So one of the things we learn in Calculus 1 is that there's a connection between increasing and decreasing and the derivative when it exists. So supposing the derivative exists, all right, then, you know, functions, how can we capture increasing? Functions increasing if what? We simply need the condition that f prime of x, right, is greater than 0 for all x in the interval. Right, if f prime of x exists for every x in the interval and it's positive, then it's an increasing function, right? On the flip side, if f prime of x is less than 0 for all x in the interval, then it's a decreasing function. I suppose, well, to be picky, you know, at the level of calculus, of course, we have a little theorem, right, which is that if f prime of x is equal to 0 for all x in an interval connected subset, then what? Then f of x is just equal to some constant, right? So I guess I probably should say strictly increasing over here. I mean, the derivative could be 0 at one point, and the function could be increasing, like, so for example, let's look at an example of that. Yeah, let's take a couple examples before I go into concavity. So example 1, let's start out real simple actually. F of x equals to, how about something real simple, e to the x, right? Well then df dx is equal to e to the x. Of course that's positive, so thus f is increasing on the whole real numbers, right? Of course you know that, right? What does this graph look like? Right? Alright. Here's the example I was hinting at a second ago. If we have f of x equals to, say, x cubed, right? Simple example, but df dx is equal to what? 3x squared. So notice that this is greater than 0 for x not equal to 0, right? But you can also see that f prime of 0 is equal to 0. Remember what that means. That means that 0, x equals to 0 is a critical number. Or sometimes, if I'm being sloppy, I'll just say it's a critical point. I guess technically the critical point is 0, 0 here. But if I draw a sign chart, right, for the derivative, df dx equals to 3x squared, well, there's only one interesting number, 0, right? And, well, you've got pluses all around, right? So yeah, even though there's a critical number, it's just a place where the tangent line happens to be horizontal, it levels out for a second, then it just keeps going, right? Of course, you may recall that the graph of a cubic just looks like this, right? Like so. So this function, right, even though it has a horizontal tangent, even though there's a place where the derivative is 0, this function's increasing on R. All right. So let's look at another example. So what I'm going to look at here in this example, guys, shh, be quiet, please. So in the next example here, let's look at a slightly more interesting function, example 3. Let's look at f of x equals to, say, x squared e to the x, all right? So here, what I want to do is I want to find the intervals of increasing decrease, all right? So, all right. So what is df dx is what? F prime of x is 2x e to the x plus x squared e to the x by the product rule. And so you can factor out e to the x, and you factor out x also, right? So I have x times 2 plus x times e to the x. Now, this is never 0, right? The exponential is never 0. Whereas this guy is 0 when x equals minus 2, and that's 0 at 0, right? So we can make a sign chart for the derivative, which is super useful in guiding our thinking about where things are positive and negative. Just like I showed you for the inequality of the polynomial in the earlier lecture, right? So, okay, so just plug in a point, right? If I plug in a positive, like something, plug in 1, for example, over here, you know, by the intermediate value theorem, this has to stay positive or negative on one side of the 0 or the other, all right? The only place it can change from positive to negative is at a 0, is my point. So it suffices to check in each subinterval to figure out what the sign is of this thing everywhere. Anyway, so plug in 1, you get positive, all right? I'm also going to get positive over here because I get a negative times a negative. But more to the point, because these factors appear linearly, I mean, appear in terms of an odd power, it's going to be the case that the sign flips at every crossing. I can tell that from just looking at the formula. So once I figure out one of these, I can automatically know it to flip sign. In contrast, in that previous example, right, this one here, there was no sign flip because the derivative was x squared, and so it stayed plus to plus. Anytime you have like the 0 is to an even power, it's not going to flip sign at the critical number. All right, anyway. So, so there it is, and then you can see right from that it's going to be what? What's the answer here? This is increasing. We have increasing on minus infinity to minus 2. You could include or exclude the 2, I don't much care. And union with 0 to infinity. And the function's decreasing. F is decreasing on minus 2 to 0. Again, if you want to write open interval there, I don't much care. Whatever floats your boat. So, increasing and decreasing, these are both concepts that are understood for sets of numbers, not at a point. I think that's something that's sometimes not appreciated enough. Okay, anyway, so there we go. That's where it's increasing, that's where it's decreasing. And, of course, you will recall the first derivative test says what? It was like a theorem, right? If f prime of c is equal to 0, and what? There's two different things can happen, right? So basically, I'll draw it graphically. That's how I like to actually calculate, but not how I usually state the theorem, but I'll state it that way here. So basically, if you look at the sign chart, right, and you got your critical number C, right, and the critical number C, the other possibility, of course, is that the one thing is the f prime of C could be equal to 0, but there's another case, right, or f prime of C does not exist, right? All right, and f is continuous. We do need continuity. If f is not continuous, then I wouldn't be able to say this. But if f is continuous, then I can say this. If the sign chart looks like, right, if it's going minus to plus as I go from left to right on the sign chart, right, versus if I go from plus to minus, well, those are two different cases, right? So then this says what? The punchline here is that f of C is what? Is a local, what? It's a local, let's see, the graph is going down and then up, so it's a local minimum. This would say that f of C is a local maximum, right? So this was the first derivative test. If you can look, you can study the way the first derivative changes signs at a critical point, right, to see whether it's a minimum or maximum. I guess there's a third thing, right, which is that if it doesn't flip signs, then f of C is at a saddle point. That was like the cubic we saw, right? That cubic is what's called a saddle point because it's, as you go one side or the other of the critical point, it's both increasing and decreasing. All right, that terminology makes more sense in 3 dimensions, but you know, we have almost all the, I mean, I've got enough here to graph, at least to make a sketch, right, of this function, so let's do it. Let's see here, so here's x, here's y. I want to try to make a rough sketch of y equals x squared e to the x using the data we found up here. So I guess a little bit of algebraic data to notice just to get us started. If I plug in 0 at 0, right, so one point on the graph is the origin. Okay, so then what else? At minus 2, what do we have? It was increasing and then decreasing. So that's this is at a max, right? At a local max. This is a local min. Let's see here. So the minus 2. See, 1, 2. All right. So at now I don't really care much what the value is. I'm just gonna kind of, this is heuristic, qualitative, right? So there's a max, and then the min is at 0, right there. And then let's see, x squared e to the x. Well, that just gets bigger and bigger, right? So apparently it does something like this. Now it's hard to know just from this much data what happens over here, right? What happens, you know, does it go like this? Just keep going down and down and down, that's why there's no other min or max? Or does it go asymptotically, right? Does it go asymptotically, I'll do it in red, to 0, like this, right? Now if we knew about limits at infinity, and you may have learned that in Calculus 1, then you know that it's actually the red path. Because ultimately the exponential wins, right? E to the x goes to 0 as x goes to minus infinity. I don't know if you've seen this before or not. We'll talk about this more in Calculus 2 again. We need to think about these kinds of limits to understand sequential limits. Anyway, the fact is e to the x goes to 0 as x goes to minus infinity, whereas x squared, of course, goes to infinity, right? So you got a battle. The x squared is getting huge, but the e to the x is going to 0. Which one wins? Well, turns out the exponential wins, all right? Now, one way we can decide which one of these cases it is by using concavity, actually. Even if you don't know about infinite limits, you can figure out whether it's this or that, basically by concavity. So the concavity, right? Well, let me. I know you guys have seen it before, so let me just go ahead and do that here before I introduce concavity properly. F prime prime of x is what? Well, f prime prime of x is going to be, let me see here if I can do it right quick. It's derivative with respect to x of, let's see here, multiplying that back out, that's 2x plus x squared e to the x. And so when I differentiate, what I get is, let's see here, I get I get 2x plus x squared from the derivative of e to the x term, and then plus 2 plus 2x from the derivative. I mean, that's product rule. I just did it in my head. So what do you got? You got x squared plus 4x plus 2, if I haven't made a mistake. Right? And, oh, great opportunity to complete the square. This is x plus 2 quantity squared, right? Minus 2 times e to the x. So what do I got? I've got x plus 2 minus the square root of 2. Oops, sorry, I'm off frame. Let me move it up here. Or x plus 2 plus the square root of 2 e to the x. So if I draw a sign chart for the second derivative, I have zeros at, possible points of inflection, as they're known. I have f prime prime of c equals to 0 for c equal to what? Minus 2 plus or minus the square root of 2, as it happens. So minus 2 minus the square root of 2, minus 2 plus the square root of 2. Square root of 2 is 1.141 blah 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 blah. So this is about minus 0.6. This is about minus 3.4, give or take. All right. And okay, well, so this is actually, if you think about this, just think about this on its lonesome. That's a quadratic that opens up and has two distinct zeros, which means that the signs for this go plus, minus as it dips below the x-axis, and plus again. This is always positive, the exponential. So as I think about the signs for this, I know it has to go plus, 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 and then minus is in the middle. All right. And that tells me, guys, where the function that we're looking at is either concave up or concave down. Concave up over here, concave down in here, concave up over here again. And all right, so this is about minus 3.4-ish. This is about minus 0.6, give or take. So let's see, let's try to put that in here. So this point, and let's see here, 2, 3, let's see here, keep going. Let's see here, so this was 1, minus 2, minus 3, minus 4, all right. So not sure I've drawn it quite right. So here, minus 3.4, 1, 2, 3. So somewhere in there, there's a inflection point. I don't know if I've done it right or not. So what I'm saying is that this part right here is concave up, right? And this part over here is concave up. You can see my graph isn't quite right. This is a point of inflection, right? And so this piece right in here, I can't, I'm bad at doing these, let's see here. So I can't do it very well, but this is concave down. It's like a downward shaped bowl in here, with that being the local max right there. But the fact that it's concave up over here pretty much forbids this happening, right? Because if it was really going down to minus infinity, it would be concave down, right? to get concave up over here somewhere, this thing would have to do something like that, you know, I think. Well, I don't know, I'm not sure it's entirely convincing. Maybe it's not. Certainly, once we have this technology, it's easier to figure that out, so I'll just leave it at that. All right. Well, I'm going to stop this and start it again with another example.